Okay. So as usual, all the materials for the bootcamp will be available at researchhub.qsandbox.com. Okay. So in the first 2 days, we got an orientation on typically what do we talk about when we talk about data science and finance. And we took a case study approach. We looked at the lending club data, and we got an introduction to the data set. We kind of did some exploratory data analysis. And then yesterday, we spent most of the time kind of understanding machine learning algorithms. Can someone tell me about the 3 machine learning algorithms we focused on or we talked about yesterday? Regression analysis, that's the first one. Random forest is the second one. Neural network. So we have an A student in here, so we should give a round of applause. So, and we looked at one unsupervised learning algorithm. Which one was that? K-means. So this, we talked about the K-means algorithm. So today, we're going to focus on a topic which is something which no one wants to do. And that's basically tuning your model. Okay, everyone wants the first model to work perfectly, and you just want to put your data in it, run through your initialization, and deploy this model. And the reason why machine learning hasn't been adopted to the extent to which it has the capabilities and the capacity is because people have not done a really good job in tuning the model before deploying it into production. Okay, so we'll kind of understand some of the dynamics involved in enabling these models and getting these models into production. And before doing that, we'll kind of look at the various levers you'll have to operate before you can deploy a model into production. Okay. So before that, I want to kind of set the stage again. So we are 50% past to this crash course. And day 3 is primarily going to be fine-tuning the models. And tomorrow, we'll talk about deploying these models. Okay. So if you look at this whole thing as a sequential process, we have gone through data preprocessing and ADA. We have built our first machine learning model. And now we'll be evaluating the various models. And I'll give you the frameworks on how you're going to be doing it. Before going there, just a quick summary of the algorithms, the supervised and the unsupervised space. We are predominantly, for this case study, looking at the prediction problem. Okay. We're not doing any classification as a part of this case study. We did a little bit of clustering yesterday, but we are not going to be doing any clustering today. We'll primarily focus on fine-tuning the prediction model we talked about yesterday. Okay. So in the context of what we are doing, we looked at the 3 algorithms our friend talked about, the linear regression algorithm, the neural network algorithm, and the random forest algorithm. Now, in the context of linear regression, what are the typical things we can potentially do is the question, right? So if you have multiple variables, you can potentially think about variable selection. Are all these variables important in the context of the prediction I'm making, right? The other thought is doing variable reduction. That would be to say, well, all these variables have important information. Rather than using all these variables, can I reduce the variable space into a smaller set of variables and use those smaller set of variables, right? And each one has its own benefits, and it comes with a cost. So we'll talk a little bit about it. In the context of neural network algorithms, it's futile to basically think about looking just at the variable space. You have to more or less think about in the context of engineering your neural network, which is to say, what are the levers you can operate to make your neural network more efficient? What algorithms can you choose? What parameters of the algorithm can you choose? And what hyperparameters can you choose when you think about optimizing an algorithm, right? And then in the context of random forests, we'll have to think about, well, what are the various things you can operate? Because this is a non-parametric algorithm, but you still have levers you can operate to figure out if you can potentially fine-tune this algorithm. As you can see, if you start enumerating these choices, the choices are just going to explode. The choices you have, it's impossible for you to possibly look at all the possible choices you have in terms of parameters and come up with the best possible algorithm. The intelligent thing to do is to understand the nature of these algorithms and figure out what levers give you the biggest bang for the buck and focus on those levers. And that could be data specific, it could be domain specific. It depends on how far you want to go and what metrics do you want to optimize. Okay? So let's kind of set the stage and understand some of the mechanics and some of the metrics before we actually dive into the case study and kind of start tuning our algorithms. Now, yesterday I briefly mentioned about a couple of metrics you would want to compute before you can figure out how good an algorithm is, right? So I'll kind of briefly touch upon those again. When you talk about performance evaluation, the first thing you need to think about is, well, what kind of an algorithm am I using? So if I'm thinking about a supervised prediction algorithm, some of the metrics you could compute are basic things like R squared, or a root mean squared error, or a mean absolute error, or a mean absolute percentage error. And we'll talk a little bit about it in a minute or so. But if your goal is to think about classification, thinking about like, my results could be yes or a no, then the goal would be to figure out, can I put together what's called as a confusion matrix? Can I think about ROC curves? Can I think about accuracy measures? Okay. So depending on the use case, you'll have to figure out what metrics to use. So let's start computing some of the initial metrics. So the simplest thing you could do is compute what is called as an error, right? So you have a model, you put in your variables, your inputs, and it gives you a value or a prediction. And then you compare the prediction against the observed value, right? And that would be your error, right? So depending on what you're doing, sometimes the error could be you're overestimating the value or you're underestimating the value. So errors could be positive or negative, right? Now, you can't just take individual errors for each one of these records and do anything with that. I mean, you can potentially look at how varied your results are. But the goal is to figure out some kind of a summary measure which tells you overall how good your algorithm is. And that's where you can compute a metric like R squared, which tells you how good your statistical fit is. But typically in the context of machine learning or in data science, R squared, just looking at historically, gives you very limited information. So most of the times, people in the context of, well, you can also look at adjusted R squared if you're working with multiple variables. But typically in the context of machine learning, people start looking at metrics like mean absolute error, right? So on an absolute level, if you take all these errors, take the absolute value of it, on an average, how much error am I going to be seeing if I use this particular algorithm? Another metric would be the mean absolute percentage error. And here what we are doing is we are taking the errors which we have been computing and taking a percentage measure. So rather than having a metric which says at an absolute level, this is what the error is, you kind of bring a percentage measure. So am I off going to be, am I 5% off or 10% off from what was expected, right? And then another metric is the root mean squared error, which you can potentially compute for both training and validation data. And then you can use that as an evaluation metric. So I've seen people compute all these metrics and kind of formulate it as a table. And depending on the use case, choose the metric, or more or less they look at all these metrics and pick and choose one of these metrics, or sometimes say, well, for a particular algorithm, I'm going to choose the best RMS value, best MAPE value, best MAE, and then sort it and then pick a particular algorithm. Okay. So in the context of prediction, this is what you can potentially do. We're not going to do any classification as a part of this crash course, but just to let you know, what you could also do is just basically tabulate your results and then figure out how many cases in the context of classification were accurately classified. And those would be your diagonal elements. And you want your diagonal elements to add up to the number of elements you have in your record data set if the algorithm is really, really good. The off-diagonal elements tell you how bad your algorithm is, which is basically telling you how your classification went wrong and which class was not accurately classified. So this is a good summary measure to figure out how good your algorithm is from a classification context. You can also do some summary measures like computing the accuracy. You can look at the misclassification rate or the overall error rate, or 1 minus the overall error rate would be your overall classification or overall accuracy. It also depends on the class of problems. We'll not talk too much about it, but if you have a balanced data set wherein you have the yeses and the nos more or less proportional, then you can potentially use an accuracy measure. But if you have an unbalanced data set where you have 90 to 95% of the data being of one class and 5% being of another class, then you'll have to look at the important class and then compute the accuracy for those important classes. Because most likely, if you're thinking about an application like fraud detection, you'll have like 99% records which are not fraudulent and 1% of the records which are fraudulent. So even if you have an algorithm which by default assigns every record to be non-fraudulent, you will still be 99% accurate. And that algorithm is going to be useless because you're caring more about the 1% of those records which were marked as fraudulent, and you want to have an algorithm which can detect those 1% of the records. So you have to look at class-based accuracy measures and then some other measures like precision recall to figure out like how good your algorithm is. Okay, so that's a little bit about the metrics. Now, just to kind of give you, again, some key points to remember when you're talking about these kinds of metrics. First of all, you have to think about the application you're choosing and the metric you're going to be applying for that particular application. So as I said, if you're looking at fraud detection, you may want to think about class-based accuracy measures. If you're thinking about any kind of prediction, you have to figure out, well, do I want to quantify the error metric, or do I want to find out some kind of a percentage number? And based on that, you're going to be choosing your evaluation metric. And then you also need to think about, well, these metrics should not just be computed on training or testing data sets. You have to compute the metrics for both training and testing, right? Because your training data, once you have built your model, your metrics are going to tell you, how good your model was for the data is already seen. And computing these metrics for the testing data set would tell you, well, if you have never seen this data before, how good your model is going to perform. And that's actually more important in the context of prediction, because the model has been built using historical data, and now you're applying it to a new data set which the model has never seen before. And is it generic enough to be able to predict what was never seen before, right? And then you also need to figure out, well, both of them should be more or less similar, right? So if your model has been trained for a particular data set and you're getting, I don't know, an error rate of 0.5%, but for your testing data, the error rate is 10%, then obviously your model is not good enough for prediction. But if it's the other way around, wherein you're seeing a training error of 10%, and for the testing data, you're seeing an error of 0.1%, then obviously something's bad with the model. You can't just use the model. You have to figure out what's actually happening. So the ideal thing would be to have a training and a testing error more or less to be similar. And then you also need to think about overfitting and underfitting, kind of on the same lines of what I was talking about before. It's very easy, pardon the typo, there was a little bit of typo there, but it's very easy to overfit models, especially with the amount of compute power we have, with the number of degrees of freedom we could potentially choose, especially if you're trying to build really large-scale neural networks. You can build a model with close to 0% training error, but it's going to be absolutely useless in the context of prediction. So you have to always think about overfitting and underfitting when you're building out these models. And the other thing which people forget is model building is not a one-time activity. Okay, it's just a start before you can start deploying this model into production. And when you build this model and you put this model into production, you're going to figure out that it's going to degrade over time, or there are going to be scenarios when this model is not going to work really well. So you have to have a monitoring process to figure out like how good your model is as you use this model in the context of prediction. And then finally, you just need to have some humility. Your best model is not the best model. Okay, so we are all restricted with the amount of compute power we have. We'll be restricted with the amount of algorithms we can potentially use. Just because we tried out n number of possible experiments doesn't mean that the model we have is the best model. So you had to engineer the process in such a way that you can leverage the compute power, the right algorithms, the right skills to build out the best possible models. And you need to have an evaluation framework to figure out how do you quantify these results and possibly get the best model into your production cycle. Okay. So just a couple of things to think about when you're building out and deploying models. Now, when we are fine-tuning a model, so once you have your metrics defined, and you know that these are the things I'm going to be observing when you're kind of building out your models. Now, the question is, how do you tune a model, right? Well, it's not an easy answer. There isn't a single recipe which you can use to fine-tune your models. The point I want to make as a part of the next 15, 20 minutes of discussion would be to just tell you the possibilities you're going to be dealing with and the choices you're going to have when you think about building and tuning machine learning models. So let's kind of discuss the process which is typically involved in building out machine learning algorithm. So we have gone through some processes already. We have skipped some of them, but I'll kind of emphasize those processes which we have skipped in a little bit. So you started with data. We did a little bit of data cleansing. We did some exploratory data analysis, but you can do a lot more. Especially this whole area of what's called as feature engineering is to figure out what kind of features am I working with, or what kind of variables am I going to be working with, and how do I engineer those features. And there you had to think a lot of different things. You had to think about missing data analysis. You had to think about outlier analysis. You had to think about, well, if I do not have certain variables in my data set, do I exclude the whole row, or think about imputing or figuring out like what those missing values are and what value should I be using as substitute values based on the other data points I have already seen. Then you also need to think about, can I derive new variables? If I've already computed certain variables, especially in the context of finance, you're working with a lot of ratios. Can I derive new variables which actually make sense rather than using individual variables? Then you have to think about, should I be doing feature selection? Should I exclude some of these features which are not important for my analysis, or should I keep all my features? And then feature reduction or feature engineering, where you're thinking about, well, can I generate new features? Can I eliminate features? Can I combine different features? So all those go in this whole area of feature engineering. Now, depending on the algorithm you're going to be choosing, you may have to do a lot of feature engineering, or you can let the framework you're going to be using decide what features it should come up with. And then the question of the whole training and testing. So I want to emphasize again, training and testing, you can't just do it as a one-shot process. We will not have the time over the next 2 hours or so to go through all the ways in which you can do things. But just to emphasize, yesterday there were some questions about why 80-20, or can we do 70-30 or 95-5? All those are experiments. It all depends on the kind of data you are working with and the nature of the data and the observations you have recorded. So you may have to go through figuring out like what different proportions may make sense for your experiments. You may also want to think about processes like cross-validation. So you're going to be saying 80% of the data is going to be used for training, 20% for testing, then reshuffle it, and then maybe using another 80% for training, 20% for testing. So you have the possibility to kind of try out different mechanisms to structure your training and testing data sets before you build out your algorithms. And then comes the question of model building. So yesterday we tried 3 models. Those are not your only options. right? Depending on the domain you're going to be working with, there are a lot more possible choices. You may have to make those choices in the context of which algorithms make sense for the application we have at hand, and how do we, bring those models into implementation and then test it out. And then comes model selection. So let's kind of briefly talk about some of the things you would want to do when you're talking about these three models we discussed yesterday, and then we'll kind of go into the case study. So in the context of regression models, so yesterday I mentioned the goal of probably using a regression model is to be able to generate these coefficients. And these coefficients are going to tell you how much influence each one of these variables has on the outcomes, right? Now, in the context of the variables we are using, we are defining the structure of the equation. So if you're saying a linear equation, then we are saying my outcome is linearly related to all these variables. So at that point, you're already making an assumption, right? So traditional statistics, we have all looked at models wherein you could say, well, if I plot it and it doesn't look like a straight line, looks like a curve, can I use a second degree polynomial? So if I say my y is a function of x squared, xi squared, or whatever it is. Or you can choose a polynomial fit, third degree, fourth degree, and you can choose multiple relationships and figure out if the fit is good. So what that means is you may have to think about transformations in your x and y variables when you're trying to build out regression equations. And then you may be even thinking about, well, I have so many variables. I do not want to use all my variables, either for computational sake or even to just figure out the important variables. You can potentially do things like dimension reduction, right? And then you can also think about feature selection. And that's where you're going to be thinking about, well, do I want to use all my variables, or can I choose a subset of my variables? And there you can think about a couple of different things. Let's say I want to figure out my most important variable. And then I'll be, if I have, let's say, 16 variables, I'm going to start putting together a framework saying my y is a function of the first variable, y is a function of the second variable, y is a function of the third variable. And then look at the whole set of variables and then come up with the best or the most important variable. And then I'm going to say I'm going to freeze on this first variable. Now, given that I'm going to be using this first variable, what would be my second variable? What would be my third variable? So you can go about doing what's called as forward selection. Or you can do about what's called as backward elimination, which is to say, I'm going to use all my variables and then think about, well, what's my best n-1 equation regression? And then which is basically saying, let me remove the first one or the second one or the third one and start eliminating one at a time and figure out like what's my best n-1 equation. And then you can think about eliminating one variable at a time. Or you can do a stepwise, which is to add variables and then remove variables, and you do it in a stepwise fashion. So in order to do those things, especially in the context of Python, Scikitlearn actually has a bunch of different functions. You don't have to implement everything from scratch. You just need to be able to choose the respective modules. Scikitlearn is a Python package, as we discussed before. So you can specifically go into looking at, well, I want to do univariate feature selection, bring in the right functions, choose the appropriate functions, and then go about implementing your respective feature selections. Okay. So I've given a link so that you can explore some of these features, and there are also some examples along the way, so you can play with those examples if you're interested. Since we're not focusing a lot on the syntax in this class, I just wanted to give you some pointers if you wanted to delve more details into that particular topic. Okay, I think we skipped some of these slides. Back. So just a quick check. How's the video? It's perfect? Good. Okay, so the next thing we're going to talk about is the random forest model. So just a quick reminder, the random forest model is an ensemble model. And what that means is we are building a forest of trees. And each tree will have a set of leaves. And we can define the depth of a tree. So what happens is all your records, when you train a model, some of these records are going to be in this leaf. Some of these will be in this leaf. And when you have each one of these leaves have a bunch of records. So based on my new data, the various variables, I'm going to go through this decision tree, if you will, and then end up in one of these leaves, right? And whatever the value you have observed in the past, you're going to take, if there are 50 records in there, the value would be just an average of those 50 values. Now, you have multiple trees you're going to be working with in an ensemble model. Now, if you just build out the first model, obviously, it'll not be very optimal. So how do we go about choosing other options? And that's where you have to start looking at what are the choices you have in building out a random forest model. The first one, there is, again, I'll show you the Python documentation. You can think about the maximum features you can potentially use. So if you have a 16-feature data set, you can say, you know what, I want to be able to use only 5 features. Think of an application, for example, your credit card application, right? So if you have a mobile app and you intend to provide loans using your mobile app, and you are trying to do customer acquisition, you don't want to give your customer 26 different questions and then make a decision whether to give a credit card or not, right? If you're building a mobile app, you'll probably be thinking about what are the most prominent 4 or 5 questions I want to ask my user before I can say whether this person is a qualified lead, so that we can go to the next step of figuring out, OK, now you can put your social security number and other information. Or should I basically deny this person a credit card based on the 4 or 5 questions you want to answer, right? So things could be like, well, what's your FICO score? Or things could be like, well, are you currently employed? Are you a resident of this particular state? Those could be some qualification criteria before you can even get to, well, give me your social security number, right? Again, it's a relationship thing. Let's say you go to Citibank and you apply for a credit card. They ask you like 26 different questions, and then once you hit enter, they say, oh, we figured out that you're not a resident of Massachusetts. We can't give you a credit card. And say, well, why would I go to this institution again? Because they just made me do all this work for nothing. They could have asked me this beforehand, right? And again, when you're talking about mobile devices, you're now talking about real estate. You can only put in 3 or 4 questions in an interface. You can't put in all the questions in a single screen. You don't want to like go through multiple screens before you can come up with a decision. So you want to present the user with the most obvious questions and the most obvious choices, so that the user can get to the next step of whether they'll get a credit card or not, right? In those kinds of things, you may have to say, I need the most important 5 features or the most important questions I want to ask before I can go and choose this particular algorithm, right? Another question would be number of trees, right? Yes, please. Right. Well, the number of trees will come here. I'll talk about the number of trees in a second. So the number of features in a tree is basically what in a tree, based on the tree you're kind of you're letting the algorithm decide what's the maximum number of features you want to use in that particular tree, which will basically come down to the 5 questions or the 5 features you want the values for, right? Yeah, exactly. Right. Yeah. So the number of trees would be what you were kind of getting to, would be to say, well, I'm building a forest, I'm building an ensemble model. So rather than thinking about one tree, I want to be able to get the majority voting or the average value of 10 different trees. So that's basically give me like 10 estimates, and then I'm going to take an average or some kind of a summary metric of those estimates, which I'm coming together. Right? So that would be the number of estimators. The third would be the minimum number of data elements in a leaf. So that's to say, well, if I have really deep trees, and then I have like one record, it's technically overfitting, right? So you're basically building out a tree which is overfitted to that one particular record, which is not something you want to do, especially if you're building a generic algorithm. So you want to prune these trees or get these trees to a level wherein these trees at least have a minimum set of records. So you would say, maybe 50 records or 30 records or whatever that number is. So you want to have at least those number of records in those leaves so that you can take an estimate based on those number of records out there. So if there are two leaves, one having 10, another one having 20, you want to kind of put them together into a leaf and basically combine those records rather than having them as two individual leaves. Okay. And then you can say a number of processes. It's more of a system kind of a thing, wherein in Scikitlearn you could say, well, I have 4 processors on my machine. I'm building an ensemble model. Rather than using one processor and doing all these things sequentially, let me use n number of processors or unlimited number of processors. Just choose how much processing power you want. It's more of a system thing, so it will make your algorithm go faster. Okay? So what that means is you have a lot of levers. And based on the choices I make, I will end up with different results, right? So the question is a design of experiments question. So, what would give me the biggest bang for the buck based on my past experience, based on the data set I'm working with, based on all the levers I'm currently using, coming up with those set of experiments you want to run so that you can do your model selection. Okay? And then again, as I said, I've given a link to the Scikitlearn random forest regressor help page, and there you can see all these parameters you can potentially choose. Okay, so the third algorithm we talked about is neural networks. So here we're going to spend a little more time because a little more understanding is required in the context of why we need to do it. And I'll kind of give you the big picture in here, and I'll give you contextually the details as we go through the case study. So the algorithm we chose, so just to give you perspective of what we did yesterday. So this is kind of the nature of the algorithm. So when we design this algorithm, we know the number of features. We know the output. So this is just a picture for classification, but in the context of prediction, there's just going to be one output node. And the goal would be to define how many hidden layers we want, how many nodes are going to be there in each one of these layers, right? And what that relates to is each one of these arrows will have a weight parameter, okay? And then there is also going to be a bias parameter. So if I just assume that there's going to be a single node, it's going to be linear regression. Just if you don't have 4 and there's only one node, all these inputs will have a weight which will go into this one particular node. So each one of them will have a unit contribution, and then you'll have a bias. So that'll be your intercept. So you'll have an intercept, and you'll have weights associated with it, which will just be a linear regression. As we add more layers, it just adds to the complexity of what those weights and biases could be. And that's the reason why a neural network is a more generic framework. And you can basically start with a linear regression and kind of enhance the complexity there. Note that what we are talking about are just parameters. It's not hyperparameters. We will have to deal with tuning what are called as hyperparameters. And because, as I said before yesterday, when we talk about linear regression, you can just basically think about it as a matrix inversion problem or an ordinary least squares regression. Simply minimize the sum of the square errors, right? But in the context of neural networks, because of the complexity, you have to treat it as an optimization problem, right? So you have to start with a random solution for these weights and biases, and then have a mechanism so that you can iterate on the changes in these weights and biases so that you can come up with minimizing the loss function. So you can set it up as an optimization function where the goal is to minimize the loss, and then coming up with the best set of parameters subject to various constraints. Now, since we are setting up an optimization problem, you have to figure out which optimization algorithm I'm going to be using, right? Typically, there's what's called a stochastic gradient descent, Adam, and a bunch of other algorithms which you have choice for. Then you have to think about the learning rate, and I'll talk a little bit about it, which is to say, am I going to be a very fast learner or a slow learner in terms of figuring out the weights? And that also depends on the context of the problem and the nature of your loss function. And then you have to think about regularization. Am I going to be penalizing when the algorithm becomes very complex? And then you also need to think about activation functions, which is to say, am I going to keep the algorithm just as a function of linear? We talked about how linear regression could be implemented in the context of a neural network. And each one of them will be a linear function if I just basically add up all the weights and biases and then kind of go to the next layer, right? So activation functions provide the ability to say, I'm going to be potentially adding non-linearities into the equation. So that's kind of the set of parameters we're going to be using. So let's move to the case study, and then I'm going to give you context on how we are going to be setting up the case study. Now, as I mentioned before, you should have all received an email for the lab. So if you click on the lab, you're going to go into the Q sandbox, and when you refresh, you're going to see a running lab. So this running lab basically has day 3 of the case study. So I'm going to launch my lab. It's currently running on Amazon. We'll launch the Jupyter Notebook. So we'll go into the work folder and go into the notebook. So you're going to see a bunch of different things. So we need you to focus on this version 2 of the algorithm. But let me start with version 1 and then go into version 2 so that we can build in the continuity. So as I mentioned yesterday, we're going to be primarily building out these 3 models. So yesterday, I showed you how to build out the linear regression model, and then the 3 metrics, the RMSE, mean absolute error, and the mean absolute percentage error. And then we built out this linear regression model. And then we chose a random forest model wherein we were setting up a bunch of criteria. We didn't say anything about max nodes. We didn't say anything about, we did mention that the depth of the tree should be 5, the maximum depth of the tree should be 5. Then got our first iteration of the model. We got a bunch of error metrics, and then we ran a neural network model. And I didn't talk about some of these options, which I'll talk about today. We specified an activation function. We specified learning rate. We specified an optimizer. And we said run through 300 iterations and come up with the best possible algorithm you can come up with. And ultimately, we said that this is the best we could do. And for the 3 models, the best model was the random forest model, right? So let's move to today's exercise, and we'll kind of start exploring this a little more. So here, so first thing, we'll kind of do what we did before, get the data set. In terms of working with categorical data, we do what's called as one-hot encoding. And that's to say, if there are choices A, B, C, and D, if there are 4 possible classes, so rather than representing them as categories, I'm going to represent them as a vector of zeros and ones. So I'll have like 0, 0, 1, 0, 1, 0, 0, 0. So these would be the representation of these particular classes. Okay. And then we are preparing the data set. We are normalizing the data like we did before. We are setting up some helper functions, which we talked about yesterday. This just computes the mean absolute percentage error. We built some visualization functions using some of the matplotlib capabilities we talked about on day 1. And we also have a function which basically, in the context of neural network, we're going to be using, and I'll talk about it in a little bit. So let me, because we talked about neural networks very little yesterday, let me start out with neural networks. So here we have the input layer, which is where we are passing the features. We are going to be using various hidden layers. And then the output layer is going to be where we are going to combine all these inputs, and that's going to be our output, right? Now, I've given you some details in here, but it's a good idea to also refer to some of the documentation you can see in the research hub. So I'll kind of start with the documentation, then we'll go into the case study. So if you click on this lab 3, neural network model evaluation, so we have put together some documentation which will kind of explain what we are going to be doing. And in the context of the particular experiment, we read the data, and the choice of the layers and the number of nodes in a layer is something you can decide. But let's get a little bit of clarity on what these hyperparameters are, which we're going to be talking about. We are basically building what's called as a multi-layer perceptron. We are not doing deep learning. We are not using CNNs or RNNs or LSTMs or GANs or any of these complex neural networks. We're just using what's called as a multi-layer perceptron. And in the context of what we are doing, multi-layer basically means we are using more than one layers. So we have the weights and the biases. These are the the various weights, and this is like linear regression, if you will, wherein you have these weights. You have the weighted sum, and then this basically is the intercept, and that's basically what we are trying to come up with if you're using in the context of regression. But then um, when we basically come up with an initial set of weights and biases and pass these inputs to the output, there's going to be a loss. And what we are trying to do here is, propagate these losses back, and that's basically using this algorithm called as a back propagation algorithm. Okay, so what that means is when we have this as a loss function, we want to minimize this loss function. And the goal is to be figuring out like how fast or slow should our learning rate be. And if I have a big learning rate, you're going to be jumping all around because you're trying to figure out like what's the best parameter. But if you have a very small learning rate, you're going to be converging to the minimum, but it's going to take a lot of time. So the analogy here is, if let's say you want to climb a mountain, right? And you want to reach the peak. And you're blindfolded, and you're trying to reach the peak. And the only thing you could do is occasionally you can ask, how high have I reached, right? And if you can't like know where you're going, you can take some random steps. One thing you could do is, because you're blindfolded and you want to be very cautious, you can take one step at a time and ask the question, where am I, where am I, where am I? And it's going to get to the top. You're going to get to the top, but it's going to take a really long time because the learning rate is going to be very, very small. You're taking baby steps to get to the top, right? Another way to do it is, you're blindfolded, but now you have this drone. And this drone can be let, and then you can like let the drone reach a particular point, and that's going to give you a GPS coordinates, and you can potentially jump to that particular point, right? So what that means is you're still blindfolded, but you let the drone go in a particular direction, and you're going to get somewhere. And if the height is higher than where you are, and then you're going to like jump to that particular point. So the learning rate could be faster. You may reach the destination or not, depending on which direction you're flying, right? So the learning rate determines whether you're going to be going cautiously, but you will get there, or you may be randomly figuring out where you may end up, which may take a lot more trials in the context of number of iterations. Okay, just a random analogy, just to kind of get an idea of what's actually happening behind the scenes. So the point here is, when you try out different learning rates and plot it out, based on the learning rate choice, your training loss actually kind of goes up and down. So you want to figure out like you need to have a minimum loss. So that's where you can figure out like based on the enumeration, I can pick the best learning rate. So you can see that for a learning rate of I think this was yeah. So this is for the first one, 0.017, which is this, for a learning rate of very, very small. We didn't really find the minimum based on the number of iterations we had. For the learning rate of 0.01, we were able to get a pretty decent set of results. And if the learning rate was really, really high, then you more or less ended up with the same prediction, irrespective of the true values you had determined. Yeah. So your learning rate determines how good your results are going to be. Another parameter is just a graphical view. Sure. Yeah. Yeah. Right. Yeah. So the thing is, depending on the choice of yeah. Right. So you could do like multi-start, depending on where you start. You can, and I mean, like you can set up a seed and you can start at a particular point, or you can like do a random start, if you will. So in the context of local and global minimums, right? So you're using an optimization algorithm. You're giving it n number of iterations, right? So it could, depending on the learning rate, if I'm taking baby steps, you may be going in the right direction, but based on the number of iterations, you may be ending up at a minimum, which could be a local minimum, right? But in the context of learning rate, if it's going to be high, then you may be able to jump around and skip those local minimums. And you may end up at your global minimum. But in the context of neural networks, because of the number of parameters you're working with, figuring out the global minimum is going to be extremely hard. You will require a lot of computational power to get to the global minimum, right? So it again depends on the loss function you're working with. And especially in data science and in finance, you're going to work with really complex functions. So it's extremely difficult to get to the global minimum. So the goal is to figure out, how do I get to a local minimum which is decent enough for a practical application? Make sense? I can discuss more stuff offline. Okay, so that's one hyperparameter you could potentially use. The other one is the choice of the optimization algorithm itself. I'll not go through it. I'll give you some links in this, and you can potentially look up some of the nature of the algorithms. Another choice is to think about penalizing whenever the number of parameters are. So that's basically figuring out your regularization parameters. The point here being, in this particular case, you have this as your model, and this is your true function. So if you choose an algorithm which shows something like this, then this could be underfitting. This could be a decent fit. And this one actually connects all the points. It could be a really good fit from a training perspective, but it's actually overfitting, right? So you can specify your alpha parameter, which is a hyperparameter in the context of L2 regularization, and then figure out what alpha actually makes more sense in terms of minimizing the loss. It's another parameter you can potentially try. Another one is the activation function. So in the context of a neural network, right? So here we are basically, let me just get to the neural network picture in here. So here, what I could do is build a function, an activation function, which says something like, if the value here, is greater than 0, only then use that value, else do not use that value. So that activation function is called as ReLU. And the ReLU function basically is a max of 0 and 1, right? So here, in the context of what we are doing, this is basically the mathematical function. It's called as a ReLU. You can specify what your activation functions could be. The point I want to emphasize is you have a lot of choices, and you need to make intelligent choices when you're designing your algorithm. Okay? When people talk about, oh, we're going to be using deep learning and AI and machine learning for our algorithms, and you're just thinking, I'm going to be using TensorFlow or Keras or PyTorch or whatever that framework is, and you don't spend time tuning your algorithm, garbage in, garbage out. If you just let the default choices in the algorithm and just say, I'm going to run my algorithms with default choices, you're not going to get the best results. So the point is, you need to really be aware of what those hyperparameters and parameter choices are, and you need to spend the time to engineer and design those experiments so that you can come up with the best possible results. Tomorrow, we'll discuss a framework in which you can actually design those experiments, because that's the most important piece, rather than just the choice of the algorithm. But you need to really be aware, depending on the algorithm choice, what you're working with. And that's where companies differ. I mean, it depends on how quantitative you want to be, how fundamental you want to be. I've given this example in many of our meetups. We worked with an energy company, and they basically had a goal of reducing the MAPE. They were aiming to get something less than 10%, and their MAPE was around 12%. And they were just using plain old regression, and they gave us their data set, and they said, can you come up with an algorithm which can give us better MAPEs? And we ran through a bunch of different algorithms like we're doing in here. We came up with a MAPE of around 8.5% for regression, around 6 or so for random forest, and neural networks was giving around 4%. So based on all the experiments we did, we said, go ahead, use neural networks for your data set. And they reviewed all the results, and they said, OK, we're going to deploy regression. Said, well, regression actually gives you worse results compared to that of random forests and neural networks. Why regression? And they said, interpretability. We need to have an interpretable model. We need to be able to look at the coefficients and understand how each one of my variables are influencing the outcomes. We can't convince our business folks to put money into the strategy if they don't understand what's actually happening in the algorithm. In a neural network, you're going to be choosing many of these parameters, which you can't really attribute to your end results. You may get really good accuracy, you may get really good error rates, but it's not going to give you the interpretable equations which you're looking for if you're making decisions based on those kinds of models. So you have to make choices based on the ecosystem, the culture of your organization, the folks you're working with. Otherwise, it's going to be a hard sell. You can't just sell people by the numbers. You have to be able to get everyone on the same page, especially when you're deploying data science applications in your enterprise. Okay, so that's a little bit about some of the algorithms in here. So let me show you the code. So when you do your lab, what you're going to be working with. So the regression, the neural network algorithm in here. So we have put in a lot of details. Kudos goes to Atharva, who's written most of the code. So basically, we have the learning rates as a vector we are specifying, and this function basically iterates through each one of these learning rates and uses this regression model, passes this learning rate as an equation. So here's the choice, right? So I've told this to some of my students before. My first job out of college was in a hydraulic excavator company, and I had to test hydraulic excavators. And in hydraulic excavators, you basically have joysticks. And you need to operate these joysticks to basically activate your boomstick and bucket. So in order to go someplace, figure out where to land, take and excavate and move it and put it into your dump truck, you need to figure out the optimal combination of the joystick movements so that you can get there. The millennials in the room have been very familiar with joysticks with your video game play, but it's kind of the same thing in here. Here you have a lot of levers you need to figure out to get to what you want to do. What I mean by that is you can't activate all the levers at the same time. You have to figure out what lever am I going to be activating to test out what possibilities are there. So that means that you have to say, well, let me try out one learning rate at a time and see what happens. Then let me try out something else. So you may have to set up a grid of possibilities and choose different combinations, and then figure out what particular combinations work best for you. So here we are choosing one at a time just for illustration purposes. And then that kind of gives you the learning rate. The graphs I showed you in the documentation basically came from in here. So you have the framework to now choose things. So you can go in here, change these numbers to something else, do a what if analysis, and run through the code, and you're going to see different results. And you can figure out which ones are the best ones for your particular use case. And then you can also figure out different optimization algorithms. Just look at the documentation and specify the optimization algorithm. So we're choosing one optimization at a time and figuring out which one works best. So this one is Adam, the blue is Adam, and the orange is SGD, is stochastic gradient descent. So you can use either one of them in this particular case. Then you can choose different regularization parameters and then figure out what actually means. If you change my alphas, what actually happens with the loss function. So you can see that based on the different alphas, how the loss function actually goes down. And finally, we are using the rectified linear unit, which is the ReLU. Mathematically, it's just max of 0, comma x. Okay? And this is the final model in here. So what it means is more than you implementing a neural network algorithm, you will be choosing the parameters which goes into the neural network algorithm. Okay? So what that means is you need to understand the algorithms and the parameters and the hyperparameters really well, so you can design these algorithms very well when you're doing your testing. Okay, so that's a little bit about your neural network. Similarly, in random forest, we want to avoid really deep trees or really shallow trees. So you can specify different depths, and you can try out combinations for different depths. And then you can, so this is a pretty decent algorithm in here. So yesterday we were looking at around 6%. So when you try out, based on this particular choice, you are getting it down to 5.95%. And then you could also look at various features in here. And this is where we are basically looking at a linear regression model and trying to build out the best possible linear regression model. In this particular case, we have certain variables which have low correlations, and you can potentially eliminate those. and you can potentially eliminate. In this particular case, we are eliminating 4 features from our equation and trying it out. So once you build it out, you are going to be getting your MAPE and RMS and mean absolute error. So the place we'll stop today is you have a framework of trying out different experiments and coming up with your error metrics, right? Now the question is, which model do we deploy? And that's going to be what we're going to be doing tomorrow. So we'll choose one algorithm or the best random forest, the best regression, and the best neural network algorithm. And obviously, you need to get this into production, right? Otherwise, it's just going to be in the data scientist or the quant's desktop, laptop, or in the cloud. So we need to choose those. And what we are doing in here is we are using a mechanism called pickle, and we are going to be pickling this algorithm and putting this algorithm into production tomorrow. Okay, so it's 4 o'clock, and it's time to stop. I can take 1 or 2 questions, and then we can adjourn for the day. Yes, please, and we'll come here. Yeah. Oh, the output is the interest rate what we are trying to forecast. Yeah, so that's the one. That's the forecast variable. Yeah. So in this particular case, there is code in here. So this particular graph, when you kind of run this model, this one we actually discussed on day 1. Let me show you the code there. I think there was just a picture which was kind of embedded in here. So here we actually had the code in here. So this was the correlation matrix that basically generates that particular graph. Yeah, please. What do you mean by, we can come up with an equation if you want. Yeah, so in the context of neural networks, right? So what we did was when we built out this in Python, you can actually get the whole matrix of weights and biases if you're using a multi-layer perceptron. And you can take a very big Excel spreadsheet, build out all your nodes, and come up with, oh, these are the weights which are going in. This is the combination. You can do that. Doesn't make real sense unless you are actually designing those algorithms. In the context of usage of these algorithms, let me show you where we actually build these algorithms. So here we were calling this models.predict, and xtrain basically gives you the variables. And when you pass this training variables, the model actually is in this. When you built out the, let me show you where we built out. So here, this MLP regressor, this is a multi-layer perceptron. So we are passing in all these things, and you come up with the model. And this model, you can just invoke the predict function and pass in the variables, and it's going to give you the prediction out there. Right. Right. Absolutely. Right, right. That's true. Exactly. Yeah, that's true. That's exactly true, because it's an interpretable model in regression. It's simple to understand. It's intuitive. In a neural network model, you can come up with a parametric, it's still a parametric model. You can come up with a really complex equation, but you can't interpret it very well. You may have to do a lot more analysis to figure out like what may be influencing things. And that's where people don't want to do it, and they'll kind of have to make a choice whether go towards accuracy or interpretability. Okay. Cool. So we'll adjourn for the day. Thanks all for coming, and please complete your labs. As you can see, every day, 25% of your grade is dependent on what you have learned in the previous day. So please keep up with the content. So do all the 3 labs. And then tomorrow, we're going to be finishing up the 4th lab. And if there are any questions, we'll be hanging around, and we can take them there. Thank you so much.